Hello guys, welcome to the short circuit it is. This is Naresh. Today we are starting a series RC circuit and we will do its AC analysis in the LTSpice by applying a sinusoidal voltage. So for this, let us look at the circuit first. So I will be taking a resistance R1 in series with the capacitor C1. The value of the resistance would be the 1 kilo ohm and the value of the capacitance will be the 1 micro. I'm applying a sinusoidal voltage of 1 millivolt peak, or like you can say 2 millivolt peak to peak, having 1 kilohertz frequency. And we will have some design perspective from this circuit. So once you do that, let us see what is the calculation for its cutoff frequency. As the cutoff frequency f equal to 1 by divided by the 2 pi RC, so the value comes out to be 159.15 hertz. So you also can calculate the gain of the circuit by using this formula, 1 divided by the under root 1 plus omega r c square. So without any further delay, let's start with the LTSpice. So I'll be opening LTSpice tool over here. Go to the new schematic, take the value of the resistance. You can do Control R to rotate the resistance in horizontal direction. Take the capacitor's value. See, now take the ground as every practical circuit required ground. Now connect these elements in series. Take a voltage source from the list of the components. Here is a component and you can take the voltage source. Now this same voltage source you will be able to convert it to the AC source. How? I'll show you. So right click this circuit and go to the advanced without setting the DC values, as the DC value would be the 0 for us. So in the advanced circuit, just go to the, you can set different kind of the signals over here. If you want to set a square wave, you can set a pulse. If you want to sinusoidal signal, you can check out for the sine. Some exponential value also can be applied for the circuit. So today we will be doing the AC analysis, so we will apply some sine voltage. So if you want to keep some DC offset voltage, you can keep. But today I'll be just taking the peak to peak value as a 1 millivolt as amplitude, and frequency would be the 1 kilohertz. That's it. You may add the delays in the circuit and phase angle as well and the number of cycle you want, but that's not needed for the now. So this is the sine wave which is applied to the circuit. As we have decided to go with the 1 kilo ohm resistance, and value of the capacitors would be the 1 micro farad. So our circuit is ready. So let's add a label for the output voltage. Go to this and select as a port output and you will be able to see it over here. Now connect this to the output. Now save the circuit. Now let us see how we can analyze our AC waveform. Now but definitely this particular circuit will have some phase shifting as well. Let us check it out. Now run this circuit over here. So firstly let us do some transients analysis for the almost 10 millisecond. Now click here to get the voltage V1 of the source. Now you will be able to see the voltage here is 1 millivolt and it is a 2 millivolt peak to peak. Even you can measure with the help of the cursor. So that cursor can be moved up and down and you will be able to measure the total current. So here also you can see the cursor 2 minus cursor node would be the minus 1.99. So I have taken the cursor 1 up. So you can take the cursor 1 down and cursor 2 up. and you will be able to see the positive value. So it is almost 1.98. That is a 2 volt. 1.99 means 2 volt. Now let us check what is the output voltage. Click on the output voltage V out. So now you will be able to see that the input voltage has more value than the output voltage. Even if you can see there is some phase shifting between the input and output. We will do some AC analysis and draw its waveform as well. But for now, just neglect it how much this phase shifting is there. Now, as you can see, this circuit is attenuator. It is attenuating the output waveform. So let's play with the some value of the resistance. Now just try to set some more different resistance value so that the voltage across the resistance will be the less and the more voltage would be coming across the resistance even. So I'll be putting some 500 ohm value, so which is less than the 1k. Now you will be able to see that our waveform has raised this value from the 4 millivolt, like 0.4 millivolt, and like from the up and down. Now suppose I keep this value as a 1 ohm resistance, so you will be able to see that both the waveforms are matching. So to see both the waveform, add plot pane. So move this input waveform above, and you will be able to see that both the phase of the both the waves are almost similar. So this input waveform also is 2 millivolt peak to peak, and the even output waveform is also 2 millivolt peak to peak. This clearly suggests that at this moment there is no voltage across this R1 resistance. It is very negligible. That is 1 ohm with respect to the 1 microfarad capacitors. Now let's plot some different plot from the AC analysis perspective. So go to the command and you can type the command like dot AC DEC for the 10 millivolt. You will be able to set the frequency. This will be the starting frequency 1 hertz, and we will be providing up to the 1 gigahertz. So 1 G. Now with this you can have some frequency response of the circuit. So now run this circuit and select this second command which we have typed dot AC DEC 10 millivolt 1 G. So it will plot the frequency response of the circuit. Now to plot the frequency response of the circuit, so decayed points I'll vanish for it now. So just print out this one. Okay. Now here this is the AC signal. To plot this frequency response, you need to right click it, and there is some small signal AC analysis there. Type 1 over here so that you will get a frequency response. Now you can see the frequency response of the circuit. I'll just take both the circuit in the similar way. So delete this plane. Now you can see that this particular frequency response is very weird. Now let us see the frequency response of our original circuit where the value was 1 kilo ohm. Now if you try to see the frequency response of this circuit, to see the frequency, click run. So you can see that from the 0 dB our output is getting down, and this is the phase angle which is finally went to the 90 degree. So let us check the what is the 3 dB frequency over here. So take this up, and at minus 3 dB let us check what is the total frequency we have. So this is the minus 3 dB, and our circuit value as set originally are like 1 kilo ohm, 1 micro ohm, and 0, 1 millivolt, and this is the 1K value is there. So this is the one, the voltage V1 is there. So with that, suppose we take the samples 1 milli, it would be great to see what would be the frequency response. So now check it out. So move the cursor a little bit down and check what is the 3 dB frequency over here. So you can see this is the minus 3 dB point where the frequency coming down is like almost 159.068 hertz. So that's what we have calculated in our circuit. So what is our frequency? Cutoff frequency is 159.15. So if you assume it precisely, it's 159. So this is the corresponding frequency, and you can see that the phase angle or the phase difference of the wave at that particular frequency is minus 44 degree. So that's what you can see in this waveform. Now to run this again and run this waveform, take this trans 10 milli, and now you will be able to run. Now you just run the V out and V in as well. So you can see the peaks of this V out and V in are not matching. So there is some phase difference. That's phase difference that what we can see is almost 45 degree or like that. So let's stop it for today. For any comment, suggestions are appreciated. Thank you for watching.